So this is our final topic is related to the stability problems. So we need to predict the status of the bodies. If the body is immersed to the liquid or just floating on the liquid surface, how stability of the bodies we have. Okay, so that's as you can see the figures, that's the conditions for immersed bodies. Okay, so as based on the figure, you see that the 2 points are quite important. The first one is the center of the buoyant force. And then in here, this textbook, we use the C point, indicate the center of buoyant force. And then the second, we can see the point G in here, which is the gravity center. Okay, so the G in this textbook, we indicate the center of the gravity force. Okay, so we have the C and G point, and how can we do? So as the sentence shown on the below, we need to consider the relative positions between the point C and the point G. As you can see, the C and G in the first case, they are located along the single vertical line. And if we consider the C is buoyant force, so we have the uplift force for the C point. And because the G is the gravity force, so we have the downward force, just caused by the gravity. So maybe I use the weight. Okay? So if your force acting along the single line, that means there is no rotation axis. There is no rotation actions because they don't have any moment. They don't have any torque. Okay? So for the case 1 and the case 2, we know that there is no any rotations actions. But if you see the right hand side of the case in here, so if you focus the case in here, you know that the body already disturbed by the force. And if you can understand the force weight going down and the buoyant force going up, and there is the offset, right? There is the offset. So you can by your right hand and you can do the cross. You know that the rotation moment in that case will to be the clockwise, right? The clockwise moment is a negative moment. Okay, you just by your right hand. And that what's the meanings? You see the initial button is here. So if the body to be disturbed, and then we will have the negative moment, that indicates the body will rotate, and will be back into the stable condition. Will be back to the stable conditions. Okay, so after you disturb the body, and you will see the moment, additional moment, and the additional moment will require to move back to the stable condition. Okay, so that's the most important thing. If your C and the G point are not along the single lines, that means there is additional moment you will see. And the additional moment will require the body move back to the stable conditions. Okay? So you just keep in mind, we have the C point, we have the G point, and we can try to predict the stability of the body. Okay? So this is another case. We consider the floating particle. And this is very famous for the ship. Okay? And the two sentences are just write down in here. The volume to the left produce the negative moment, and the volume to the right produce the positive moment. So what are the meanings? So as you can see there, I highlight the right and the left. So if I only consider the volumes on the right, and the red dot is our centers, and maybe I consider there will be have the buoyant force, okay? And maybe I can consider the rotating hinge point in here, and the length, the arm length, this is my length. So if with the length direction cross the buoyant force, you just by your right hand, you will have the counterclockwise rotation, right? You will have the counterclockwise rotations. And the counterclockwise rotation is the positive moment, okay? So if you can understand why I say the volumes to the right will produce the positive moment. And if you go to see the left, so we have a left region in here. And again, we have the buoyant force, maybe at these locations. And we have the arm for directions. And you also, by your right hand and R cross F, you will have the clockwise rotations. You have the clockwise rotations. So that's the negative moment, right? Because the direction is into the paper. Okay, that's why the left-hand side, the ship can have the steady conditions, has the stable condition, because the right is the positive moment and the left is the negative moment. That's a moment always balance each other. So that the ship can just stand there. But the right hand side are different. That means we have some disturb. We just disturb the ship. And the disturb the ship, after the disturb the ship will have rotations. Okay? And then right now the rotations, you can see the some volumes submerge into the liquid, and some volumes just uplift the liquid. So there are some different contributions. But if you consider the regions in here, we have the upward buoyant force, and we still have the downward weight. So we have the counterclockwise rotations. We have the counterclockwise rotations. And this rotation will move the ship back to the stable conditions. Okay? So just the moment balance, and only the one purpose we would like to back to the stable conditions. Okay, and then one very important point in here, I call that the M. What are the M? In here, we call that the meta center. So not only the C and G point are important, we still have the additional point, we call that the meta center, and the M. So in the following slide, I will go into detail to introduce how can we determine the M point, and how can we apply the M point to predict the stability problem of the body. Okay, so this slide just shows all the steps for the stability analysis. So totally we have the 4 steps, and I just use the Chinese words to make the interpretations for the step 4. So from the step 1, we know that the alpha angle is our rotating angles after the disturb the ship. And the C is your centers of the initial buoyant centers. And after you have the alpha angle rotate, the C will move to the C prime. So you can see the figure showing here, we have the C prime after you rotate the alpha angle. And we draw the second step is we draw the vertical line. So we draw the vertical line passing through the C prime. We draw the vertical line passing through the C prime. And then we will see that the crossover point with the original y-axis, we define this crossover point is our meta point N. Okay, so the step 2 is we draw the vertical line passing through the C prime, and then we can find out the crossover point with the original y-axis. And this point we call that the meta center. Okay, we call that is the meta center. And the third step, what I say, and after we draw the meta center point, and we will compare the meta center point with the G point in here. So we have the G point in here. What is the G? G is the gravity center, right? So we have the G point in here. And the third step, what I say that if the N location is above G point, and we will have the counterclockwise moment. That means the ship will rotate to the stable condition, right? Because the alpha angle is rotating to the right, but we will have the counterclockwise moment to move the ship to be the stable conditions. Okay, so the third step, what I would like to say is we just consider the different locations of the G and the N point, and we can predict the stability. So the final step, in other words, the different condition N is beneath the G point, and then the ship will clockwise rotations. If the ship continues to clockwise rotation, that means the ship will collapse, right? So that's the important idea is the GN distance. We should compute the GN distance. If G above the N, that indicates the GN condition is larger than 0, right? And I call that the ship is stable. Because the GN distance larger than 0, that indicates we have the counterclockwise rotation. And the ship will be back to the stable. But if the GN less than 0, and we will say that we are unstable, because we have the clockwise rotations, and the ship will collapse and submerge into the water. Okay, so the GN distance is our good indicator to predict the ship stability. Okay, so we just consider how large the GN distance. If the GN is positive or GN negative, and we can say the stable or unstable status. So if you go back to see, the GN distance is this one, right? And sometimes it's very difficult to compute the GN distance. So we will use the CN distance minus the CG distance, and will equal to the GN. So the idea is we first compute the CN distance. Or maybe I use the blue line. The blue line in here is the CN distance, okay, in here. And minus the red line is the CG distance. And then will equal to the GN distance. So the idea is it is very difficult to find out the GN distance directly. So we can just try to find out the CN distance and find out the CG distance. And the CN minus the CG will equal to the GN distance. and we just identify the Gn is positive or negative, and then we say the particle is stable or unstable. Okay, so the following slide, I wondering to tell you how can we compute the Cn distance and the Cg distance, and then we will have the Gn. Okay, so right now we're trying to figure out how can we compute the Cn distance. So please keep in mind, we're wondering to compute the distance along the Cn. So this is what our purpose, the line length for the Cn we want to compute in our case. So we start from the moment balance again. So you can see the equation showing here. What the x bar? X bar is the difference between the C and the C prime. So we have the x bar. X bar is the equal to the C prime distance. Okay, and we have the volume V here. What are the V volumes? The V volumes is the displaced volumes. So we only, after the rotations, the displaced volume is here. That's the yellow regions. Okay, so the yellow regions in here is our V. Okay, so that means if you multiply the x bar with the displaced volumes, and then that means the total moment, right? The total moment. But we don't see the gamma, okay? Because both sides we have the gamma, so we cancel out the gamma value. If we multiply the gamma here, the equation x bar multiply the gamma V, and the gamma V here is the FB, right? So that's the Bouillon force multiply the x distance. We will have the total moment in that case. Okay, and the total moment will equal to the sub moment, will equal to the sub moment, sum of the sub moment. Okay, so what are the sub moment? So we will have the original moment. This is the original moment. This one is the original. What is the original? Original is the ship didn't rotate with the alpha angles, just stand here there. Okay, so the original moment will minus, you see that is a minus, right? Why it is the minus? Because you see that's caused by the volume change. There is the volume change. The volume change, there is the volume A or B. Okay, and as I mentioned, the volumes to the left, always the negative moment. So here I use the minus because the left, the volumes produce the negative moment. So I use the minus, and you see there is a positive. The reason why, because there is the EOD. The EOD, where is the EOD? So the EOD just the region in there. Okay, the EOD is the volume contributed by the right side. So that the right side always produce the positive moment. Okay, so but initially the original volumes showing here, there is no additional moment, right? Because the original just stem layers, it's a steady state. So that's the original is 0. So the moment contribute from the original is 0. So finally, we only have the AOB and the EOD moment contributions. Okay, and but you see the minus for the AOB, if we change it to the equation here, there is to be the positive. There to be the positive, because if you take a look at the left-hand side, the volume is uplift to the liquid. That means indicates the negative moment will decreasing, right? Because the left left volume is uplift to the liquid. So the negative moment on the left will decrease. So that's the minus and the minus to be the positive moment. Okay. So finally we know that the total moment x bar multiply the displaced volumes will equal to the AOB x dV integrate and plus the EOD x dV. We just integrate all of the volume changes and contribute to the moment. Okay? But right now, what is the dV? What is the dV? So the dV is a small amount of the volume changes. Okay? So if you can go back to see the cartoon figure showing here, if we have the small area multiply the height h, and we will have the dV multiply the height h. So dV small amount of volume change will equal to the h is the height multiply the dA. Okay. So what is the h here? H is as you can see there is the x. So the h divided the x will equal to the tangent alpha. This is the alpha angle in here, and then we have the h and we have the x distance. So the x over h is equal to the tangent alpha. So we actually know the height is equal to the x tangent alpha. So we just put the h equal to the x tangent in here and multiply the dA. And then we can rewrite the equation, the x bar multiply the total displaced volumes of the body will equal to the AOB x squared tangent alpha dA multiply the EOD x squared tangent alpha dA. Okay, so we just write down the final equation in here, and then you can take the tangent alpha outside. You can take the tangent alpha outside. So here I rewrite the equation x bar multiply total displaced volumes will equal to, I just take outside the tangent alpha, and inside I only have AOB integrations x bar x squared dA plus the EOD x squared dA, right? Okay, and right now I do exchange. I exchange this portion to be the second moment, but related to the water nice. You see a different integration region in here. Is I replace the integration region to the water line. Okay, that's a different. I would like to replace the second moment of the EOD and the AOB to be the water line area integrations, the second moment. Okay, so that's why I can do that. If you take a look, if I do the integration water line, so that here is the area, but I compute the water line integrations for the second moment problems will equal to the AOB and the EOD. So the AOB is here and the EOD is here, right? And then I also need to plus the water line contribution area is the AOEIF. So you can see we have the AOEIF. Where is the AOEIF? The EIF is this region. Okay, and I also have additional waterline area is a BODJH. So where is the BODJH? The BODJH. Okay. So I need to integrate all the contribution for the waterline for the second moment computations. So, but I highlight some idea here. Because the AOEIF and the BODJH are the pentagon shape, and theoretically for all of the pentagon shape, their second moments are always equal to 0. So we don't have the second moment items for these two integrations because their shape is the pentagon. Okay, so that's why I can tell you the I second moment here for the waterline area will equal to the AOB integration second moment and the EOD integration second moment. So that indicates finally I can rewrite the equations because there is a X bar and the total displaced volume will equal to the second moment of the waterline area multiply the tangent alpha, as I showing here. Okay. So right now I wondering to deal the problem with the left hand side. So I wondering to deal the problem for the left hand side. X bar multiply the total volumes, total displaced volumes. So that's the key questions is what is the X bar? What is the X bar? So you can see there is the X bar, right? And initially, I wondering to know how length the Cn. So you focus on the Cn and the Cc prime. You know that the Cc prime is equal to the X bar, and the Cn distance over the X bar will equal to the tangent alpha, right? Because here the angle is the alpha angle. So the tangent alpha will equal to the X bar divided the Cn distance. So we know that what the X bar? The X bar is equal to a Cn distance multiply the tangent alpha. Okay? So you put the X bar inside this equation, we can replace the X bar by the Cn multiply the tangent alpha multiply the total displaced volumes. It will equal to the second moment and the tangent alpha. Okay? So you can cancel out the tangent alpha. So the Cn distance are not corresponding to the alpha angles. So finally, we know that the Cn length will equal to the second moment divided the displaced volumes. Divided displaced volumes. So that's why I would like to tell you it is very difficult to compute the Gn distance, but we can compute the Cn distance first. And the Cn distance minus the Cg distance, and we will have the Gn. And we just identify the Gn is larger than 0 or less than 0, and we can say the body is stable or unstable. Okay, so most important thing is you should keep in mind how can we compute the Cn distance. And then the Cg distance is always easy to compute. And based on our exercise, you will know how can we compute the Cg distance. Okay, so that's our final purpose is just identify the Gn larger than 0, and we say that the stable. Okay. But if the Gn less than 0, and we say that is unstable. So the key knowledge is if we can compute the Gn is the metacentric high, and then we can predict the stability problem. We can predict the stability problem. And we cannot directly compute the Gn. So we should compute the Cn first. And the Cn is defined by the second moment divided the total displaced volumes. And right now you don't know how can we compute the CG distance. So we just based on the exercise and teach you how to compute the CG distance. Okay, so we have a very simple exercise. I just put the block wood. And the block wood have the square size is 30 centimeters. And the length of the block wood is the 60 long, okay? And we know that the total weight of the wood is the 318 Newton, okay? So I can write down some information. I have the total weight is 318 Newton. And because right now the wood is float on the liquid surface, so that we can assume right now is the balance for the buoyant force will equal to the total weight of the wood, right? Because the wood just stand there. And then the questions we need to answer will the block float with the side vertical as shown. That indicates if right now the condition, the block is stable or unstable. So you can predict, you need to predict the stability problem in this case. So let's first we need to find out some important things because there is displaced volume, right? There is displaced volumes. And the center of the displaced volumes is our C point. The center of the displaced volume is our C point. And we should have the G point, right? The G point is the gravity point. That means it's the centers of the block. So the center of the block here, the length in here, the red line is 15 centimeter, right? Because it's half of the width of the block. But right now we didn't know how the C length to the buttons. Okay, so we need to know the total H because we need to know the submerged depth for the block. And then we know that the distance in here is half of the depth, right? It's half of the depth. So we didn't know the depth submerged into the liquid. So we should compute the H first. And then we know that the C distance, okay? And I should put this is a G point. So that's the idea, we should compute the CG distance first. And if we have the Cn distance, and then we can predict how large the Gn value. Okay, so based on the first equations, we know that the buoyant force is related to a gamma and the Fd. Fd is displaced volume, that's the yellow color regions, and will equal to the W. But we didn't know the total displaced volumes. But we know that the gamma, we know that the W, so we can compute the answer. So the W in here is 318 Newton, and divided, the gamma here right now is the water. So we know that the 9A110 and the Newton meter cubic. Okay, so we can compute how the displaced volumes we have. So that's the volumes is equal to the 0.0324 meter cubic, okay? And because we didn't know the H, so we know that the displaced volume will equal to the width here. So we have the width is 0.3 meters, and we don't know the height, okay? It's fine. And we know that the length of the block is the 0.6 meters. And then we know the finally that will equal to 0.0324 meter cubic. So you can compute how large the water depth, the depth submerged into the liquid we have. So 0.0324 divided 0.3 and divided 0.6. So that's the H will equal to the 0.18 meter. Okay, and then you can convert to the centimeter is 18 centimeter, right? So right now we already have the H. So we know that the distance 2 over H is equal to the 9 centimeter, right? And we know that the distance in there is the 15 centimeter. So we can compute the CG distance will equal to the 15 centimeters minus the 9 centimeters will equal to the 6 centimeter. Okay, so we have the CG values. Why we need the CG value? Because that based on the equation, we know that the GN distance will equal to the CN minus the CG. Okay, so we have the CG information, but we still didn't know the CN distance. Okay, so the next step, we need to compute the CN distance. As the previous slide, we know that the CN distance will equal to the second moment, right? The second moment of the water line area divided the displaced volume, right? And then based on this equation, we already know the displaced volume in there. Okay, so we need to compute the I, how large the I is the second moment of the water line. So right now the water line, the shape for the water line plate, I know that the length, this is our length. The length is 0.6 meter, right? And the water line area is this area, and the width in there is 0.3 meters. So that the yellow region is our water line areas. So this is a right angular plate. And we know that the second moment for the right rectangular plate is the 12. And right now the rotation axis is along the long length, right? So that's the dash line is our axis for rotating. It's our axis for rotating. So the 0.6 length is parallel to the rotation axis. So we use the 1 power, and the width 0.3, I use the cubic powers. Okay, so you can use your calculator to compute the answer. Okay, I check from my calculator is cubic powers, and then multiply the 0.6 divided the 12. So the I is equal to the 1.35 10 minus 3 power. It's a meter 4 powers. Okay, so we put the answer back to here, the 1.35 10 minus 3 m 4 powers divided the total volumes displaced is 0.0324 meter cubic. So you can compute the CG length. Okay, 0.0324. It's around the 0.0417 meter. So the cm you can convert into the centimeter unit. It's 4.17 centimeter. So we need to compute the GN distance, right? So what are the final answers? So we just pick up the equation in here. So the GN will equal to the CN minus the CG distance. And the CM is 4.17 centimeters minus the 6 centimeters. And will equal to the minus 1.833 centimeters less than 0. So I can say that the block is not stable because the GN distance is less than 0. Especially along the rotation axis is the longitude axis. It's along the length of 0.6 meters. Okay, that's caused by because the rotation axis is along the longitude length. Okay, so this is idea is quite simple. You just compute the GN distance and identify is positive or negative, and then you can make the comment for the stability problems. So I say that the less than 0 so unstable, but the larger than 0 I can say that it's stable. So for these questions we can say the block is unstable because the GN value is less than 0. Okay, so as I showing here, so the final exercise is because the wood is not stable, so the wood start to rotate. And after the rotate, the wood with this shape, okay? And we should predict the stability again. In that case, the wood is stable or unstable. So that's the questions is very good because we already know the CG values. Because this point is the G and the cross is the C. So the CG distance already provided by the questions is 5.73 centimeter. So we only need to compute how large the CN distance. And the CN distance, we should compute the I and the displaced volume, right? But right now, what is the I? The I is the water line area. So we should know the length here. Okay, because we didn't know the length in here, that's maybe I say that the yellow line is the W. So we need to know the W. Because right now the water line surface is the length, the width here is the W. And the length still the 0.6 meter, right? So we need to understand how large the W. And then we can compute the I will equal to the 12 over 0.6 and the W cubed, right? But right now we didn't know how large the W length. Okay, so how can we know the W length? Because we go back to see the force balance is buoyant force will equal to the weight, right? And we know that the buoyant force is equal to the gamma multiply the VD, and the previous slide we know that the VD displaced the volumes is I remember 0.0324. Okay, so 0.0324 meter cubic. So we know that the displaced volume is this value. So that means the area, the volume beneath the yellow line is equal to the FD, the VD. So we recalculate we know that the volume on the top is W, and the triangular height is 2 over W. The triangular height is 2 over W. So we can compute the volume on the top is the W multiplied 2 over W and divided 2 over 1. Because this is a triangular area. It's a yellow region, blue region, a triangular area, and the multiplied length is the 0.6 meter. So we know that the top, the volume is 0.6 divided the 4. So that here is 0.15 W squared. Okay, so the V is the top volumes. So we know that the total volumes is the V total minus the V will equal to the displaced volume, right? So what is the V total? The V total is the block total volumes. The block total volume is 0.3 multiplied 0.3, and the length is 0.6, and minus the top volumes 0.15 W squared, and will equal to 0.0324. Okay, so just based on this equation, you can find out how large the W squared. How large the W squared. So I based on my calculator to compute the answers. So 0.3 multiplied 0.3 multiplied 0.6 minus the 0.0324, and divided 0.15, it will equal to 0.144, okay, meter square. So you can take a root. And the answer W is equal to 0.3794 meter. Okay, so you can know that you have the W, and then you can just put the answer, go back to calculate how large the second moment we have in our problem. Okay, so that's we have a time limitation, so you can compute the I based on your side, and then finally you can put the I go back to here, and you can compute how large the CM distance you have. How large the CM distance you have. Okay, and then you can finally identify the GN distance in there should be larger than 0, and you can predict the block will be the stable. Okay, after the rotation. Okay, so that's some ideas you can just apply to stability predictions. Just based on you need to compute the GN distance and identify the GN is positive or negative, and then you can say it's stable or unstable. And I just emphasize again the GN distance will equal to the CM minus the CG distance. And the CM is equal to the I second moment divided the displaced volumes minus the CG. And the CG distance always easy to identify based on our problem, because our problem always the symmetry shape. So the symmetry shape is very easy to identify the point of the C and the G. And you only need to know the second moment, and then you can compute the GN values. You can compute the GN distance. Again, and the GN, if the positive, and then we say that the stable. Okay, if the negative, we say that the unstable. So that's all for the prediction problems. Okay, so we may stop here.